use to build AS maps. So you can see how different autonomous systems on the internet connect to one another. And this is just a subset of the connections, so you cannot guarantee that you're seeing all the connections, but you're seeing a fair number of them. So you can use this information to build the connectivity map of the internet at the autonomous system level. There are some routing assumptions that we will use that mostly hold in the internet. The first assumption is that all hosts within an AS will follow the same path to a given destination. What this means is if I have one big AS, all the hosts going to, say, Amazon.com will take the same exit router out of this AS and go the same path. And this is mostly true. It's not true for very large ASs that are nationwide, have nationwide networks, because for them, there are different exit points depending geographically where the host is. Some exit routers are closer than others. And our analysis would work even if we didn't have this assumption, but it would be more complex. I would have more points there because I would have to break ASs into smaller networks. The second assumption is that the ASs advertise paths they take themselves. What this means is just a way that I have to guess routing. So once I have my AS map, I have to guess all the routes that all sources take to all the destinations. And I have some BGP information, so I have some paths, but I don't have all the paths. And what I can do is I can use shortest route guess, so I can infer shortest routes and say these are the true routes. And then to use BGP information, if I have a BGP AS path that goes 1, 2, 3, 4, what this really tells me is that AS1 goes over 2 and 3 to reach 4. If I have assumption 2, this also tells me that AS2 goes 3 to reach 4, and then AS3 reaches the 4 directly. And so that's mostly true in today's internet. The third assumption says there's a single path between two ASs. Again, if we had multiple paths, we could do the analysis, but it would be more complex, and I'm not showing that here. So how should I choose my filters? If I could choose any 5 or any 10 points in the internet, what would be the best points to choose? And the simplest way to grasp this is to think of the three-dimensional space. Think of a cube, and then one dimension are all the zombies in the internet. The other dimension are all the possible victims, and the third dimension are all the sources that can be spoofed. So what I should do is for every possible filter, I should figure out how big a chunk of this cube is taken out because of my filtering. And then I should pick a filter that takes the biggest chunk out of this cube. And so let's say I'm picking the top one. I would do my analysis. I would see how many triples of zombie victim spoofed address are not possible because of this filter. And then I would say, I would do this for every possible filter. I would pick the top one that takes the biggest chunk amount of this cube. And then I would take this chunk physically out of the cube. So now the cube is smaller. And then I would repeat my analysis for another filter. And that would be the ideal way to pick top filters. Unfortunately, that takes a long time to compute. It takes several days to get first 2 or 3. So that wasn't the good way to go about choosing filters. And we came up with a heuristic that gives a similar answer, but it's much faster to run. What we did is for every filter, we evaluated how good it would be filtering the portion out of this cube. And then we came up with a score that tells us how big a portion of a cube we filter. We would also then look at number of neighbors of this node and multiply this by the score that we got. So we would get a new score, including the number of neighbors in this picture. Based on this score, we would pick the top filter. And when we pick the top filter, we would take it out of the equation and we would repeat the game. It looks similar to what I told you before. What is different is that in the ideal choice of filters, in the top choice where I'm choosing optimal filters, I have to evaluate every candidate alone. So I have to let every candidate be the only filter on the internet, evaluate how good it does, then go to another candidate. And so that takes a long time. In the second approach, what I'm doing is I'm evaluating them all at once, and then picking the top one, removing it, and then evaluating them all at once again. And I'm getting pretty much similar choices. Intuitively, if you think what should be a good filter without going through all the analysis, think of all the nodes that have a lot of neighbors. They are good candidates because they have a lot of neighbors, which means that they can differentiate between a lot of paths. If I only have one neighbor, you know, there's nothing to differentiate. I cannot filter anything because everything comes on this one path. If I have 1,000 neighbors, I have a lot of options to differentiate between. Also, if I'm on a popular route, I'm a good filter. That's because if I'm on a popular route, a lot of traffic goes through me, so chances are a lot of spoof traffic will go through me and I'll be able to drop it. If I'm not on a popular route, then you know, I could do my filtering, but who cares because nothing ever goes through me. And so the combination of the popularity and number of neighbors is a good, makes a filter, makes a node good choice for filter. Okay, so we will now look at how different measures change when I take top N filters and I do route-based filtering on them. There are three measures that I'm giving you here, and the first one is something I'll call spoofability, and it's really just a number. It's averaged along all the three dimensions, the zombies, victim, and spoofed address. So it being an average, it doesn't tell you the whole picture. It tells you on the average how good the situation is, but it doesn't tell you whether it's good for everyone or it's good for a selected few, and it's really bad for the rest. But it's a single number, and so single numbers are a nice thing to plot. So I'm giving you that one. It's a percentage of triplets that are still possible even though I'm doing filtering. So out of this cube, how big chunk is remaining with my filters in place? It's a number between 0 and 1 and 0. Numbers close to 0 are good. Zombie index is another measure, and it looks at all the possible addresses being zombies. And then for a given zombie, it looks at the average and the maximum number of spoofed packets that could reach any destination. So for the average, I'm going to average it over all destinations. For the maximum, I'm just going to pick the destination that is so unlucky that this zombie can send a lot of spoofed packets to it. And then I'm going to take this measure and I'm going to average it over all the zombies. So you see there's a lot of averaging going around. Intuitively, zombie index means if I picked my zombie randomly and I let it do random spoofing, and then I picked my destination randomly, this is how much traffic should reach this destination. Victim index is something similar to zombie index. So for victim index, I take every address to be a possible victim. And then I look at every other address being a zombie, spoofing randomly packets to this one. And I take the average and the maximum number of spoofed packets that would reach this victim from any given zombie. So for the average, I average it over all the zombies. And then I take this for all the victims and I average it over all the victims. So again, I get the number between 0 and 1. This shows you if I randomly picked a victim and then I randomly picked a set of zombies and let them send spoof traffic to this victim, how much would reach the victim? Again, on the average. So a lot of averaging going on. This is the figure that shows spoofability. The x-axis shows number of filters, and then the y-axis shows the spoofability between 0 and 1. And I'm showing you 5 lines for different years, so you can see how this changes over a year. Years are between 2001 and 2005, and then purple line is 2005.